Imagine holding a tiny speck of gold so small you'd need a powerful microscope to spot it, and then finding that it melts at just a few hundred degrees Celsius, even though bulk gold doesn't go liquid until 1064 DCC. How can a material turn solid to liquid hundreds of degrees below its normal melting point? Welcome to the mystery of melting point depression in nanoparticles. Have you ever noticed how snowflakes disappear faster on a dark rooftop than on frosty glass? That happens because tiny ice crystals absorb heat more readily at their surfaces. In nanoparticles, the effect is even more dramatic. As particles shrink, the fraction of atoms sitting on the surface soars. Those surface atoms have fewer neighbors holding them in place, so they require less energy to break free. Question: just how much smaller does a particle need to be before its melting point drops significantly? If you take gold particles down to a 5 m diameter, about 20 atoms across, the melting point can fall to around 600 DGC. Shrink them further to 2 mm, and they might liquefy near 300 DGC. That's a depression of hundreds of degrees, all because surface to volume ratio climbs steeply as size shrinks. What's the physics behind this? It's called the Gibbs-Thomson effect. The equilibrium between solid and liquid phases shifts when curvature becomes extreme. A convex nanoscale surface has higher chemical potential, so the solid phase becomes less stable. In plain English, the skin of the nanoparticle is always trying to turn liquid, pulling the whole thing along at a lower temperature. Can we see this in real life? Absolutely. Tin nanoparticles a few nanometers wide can be liquid at room temperature, an effect known as cold soldering. Engineers harness this in printed electronics. Tiny solder particles fuse at low heat, wiring circuits on delicate plastics without melting them. In catalysis, platinum or palladium nanoparticles sinter agglomerate at far lower temperatures than bulk metal, limiting their lifetime, so scientists coat them with stabilizers to raise their melting point. Why does this matter? Because when you shrink materials to the nanoscale, they behave like entirely new substances. Softer, more reactive, and more fleetingly stable. By understanding melting point depression, researchers design better catalysts, low-temperature solars, and phase-change materials for heat buffering. It turns out that in the land of the tiny, the rules we took for granted in the bulk world all melt away. Sometimes literally. Opening doors to technologies that work where big materials simply won't. Nanoparticles tend to melt at much lower temperatures than their bulk counterparts, sometimes by hundreds of degrees. This surprising behavior arises because the surface properties of very small particles dominate over their internal volume properties. Atoms on the surface are less tightly bound and more reactive, making the entire structure easier to melt. As the particle size decreases, the proportion of these weakly bound surface atoms increase. This leads to the entire nanoparticle becoming thermally unstable at lower temperatures. Gold nanoparticles, smaller than 3 nanometers, melt at about 400 DGC, far below the 1064 DGC melting point of bulk gold. It's like a snowflake that melts faster than a snowball because it's more delicate and exposed. In large materials, most atoms are surrounded by neighbors, which stabilizes them through strong bonding forces. In nanoparticles, many atoms lie on the surface and have fewer neighboring atoms, making them more loosely bound. These surface atoms contribute less to the structural cohesion of the particle. As a result, the average energy needed to melt the structure decreases. The smaller the particle, the more pronounced this weakening becomes. Tin nanoparticles as small as 2 nanometers have been observed to melt at nearly 80 DFC, lower than bulk tin. It's like trying to hold together a group of magnets. Fewer connections make them easier to pull apart. Thermodynamic principles show that the melting point of a particle decreases as its size becomes smaller. Due to the higher influence of surface energy, a curved surface adds internal stress and energy, making it harder for the solid phase to remain stable. This added stress from curvature means that less thermal energy is needed to trigger melting. Essentially, small particles experience more surface pressure, destabilizing them. This effect is strongest in particles below a few nanometers in diameter. Silver nanoparticles exhibit a decrease in melting point proportional to how curved or small they are. It's like bubbles popping more easily when they're small, because their curved surface holds more tension. Because nanoparticles have highly curved and exposed surfaces, their atoms tend to be more energetic and less stable than those in flat bulk materials. These surface atoms are more mobile and can be disrupted more easily by heat. This causes melting to begin on the surface and proceed inward, a phenomenon known as surface premelting. The smaller and rounder the nanoparticle, the greater the instability. This is why particles often soften from the outside in, well before reaching the bulk melting temperature. Lead nanoparticles exhibit partial surface melting tens of degrees before the entire structure melts. It's like chocolate beginning to melt at the edges when touched long before it becomes fully liquid. Atoms in small particles vibrate more freely than those in a large, rigid lattice. These vibrations or thermal motions can destabilize the solid structure, especially near defects or edges. In very small nanoparticles, such atomic movements are enough to cause early onset of melting. Additionally, imperfections common in nanoparticles act as weak points where melting begins. These factors collectively lower the overall energy barrier for the solid to liquid transition. Studies show silver nanoparticles melting from localized regions associated with surface defects or grain boundaries. It's like a zipper that starts to open from a snag or broken tooth. It unravels from the weak point first. When nanoparticles become extremely small, on the order of a few atoms, their behavior starts to reflect quantum mechanical effects. At this scale, energy levels are no longer continuous, and both electrons and vibrations are confined to specific states. These quantum restrictions affect how heat is absorbed and spread within the particle. This makes the material even more sensitive to temperature and can cause melting at unpredictably low thresholds. Such behavior deviates from classical thermodynamics. In clusters with fewer than 100 atoms, even the addition of one atom can dramatically alter the melting temperature. It's like a musical instrument so small it can only play certain notes. And one string change alters the tune. The melting behavior of a nanoparticle also depends on what it's sitting on or surrounded by. Particles on a solid surface may stick more tightly and melt at higher temperatures, while those suspended in a gas or embedded in soft material may melt more easily. Gases, moisture, or chemical coatings can also destabilize surfaces or affect energy flow. In some cases, surrounding materials can insulate the particle, delaying melting. In others, they act as catalysts. This context sensitivity is unique to nanoscale systems. Gold nanoparticles in a silica matrix remain solid at higher temperatures than those exposed to air. It's like butter melting faster on a hot pan than on a cold plate. Depends on what's around it. Understanding melting point depression is crucial in designing nanostructured materials for real-world applications. Lower melting points are exploited in fields like flexible electronics, catalysis, and printable circuit inks where low heat is essential. However, this also limits the thermal stability of nanoscale devices, especially in high-performance or harsh environments. Controlling size allows engineers to tune the melting behavior for specific needs. It's both a tool and a constraint in nanotechnology. Low-melting nanoparticles are used in printable electronics to form circuits on plastic at safe low temperatures. It's like using quick-melt cheese. It's perfect for fast meals, but melts too easily in hot weather. The dramatic reduction in melting temperature for nanoparticles shows that materials behave fundamentally differently at small scales. Surface tension, curvature, quantum effects, and environmental interactions all combine to make nanoscale melting a unique thermodynamic process. These insights challenge traditional models and require new tools to predict behavior. By mastering these rules, scientists can engineer nanomaterials with precise thermal property. Ultimately, shrinking materials doesn't just change their size, it reshapes their physics. Researchers now design nanoalloys with specific melting ranges by manipulating particle size distributions. It's like rewriting the recipe when ingredients get smaller, because heat cooks differently at that scale.